Hello, everyone. This is Group 6, which includes Cameron Hicks and Timothy Jenks. And welcome to our Aerospace 1601 Glider Design, Build, and Fly project. In this video, we'll walk through the requirements, our design process, major iterations, stability analysis, performance results, and final iterations and reflections. So, the requirements. Our project had several strict requirements. The glider needed to be over 50% balsa wood by weight, have a minimum aspect ratio of 5, and stay under a maximum wing loading of 0.5 grams per centimeter squared. It also had to fit inside a 16 by 16 inch box, be hand launched only, and not have any sharp or unsafe features. Finally, to count as a successful design, it had to fly at least 20 feet during testing. Our design process followed five main steps. First, we identified constraints and requirements. This helped us choose targets for wing size, aspect ratio, and allowable weight. Second, we made quick paper sketches with approximate dimensions and a concept layout. Third, we laser cut the parts and assembled a glider from balsa wood. Fourth, we conducted multiple test flights to evaluate stability and distance. And finally, we iterated, adjusting the center of gravity, the center of mass, wing alignment, and tail sizing to improve performance. And then for design and iterations, our preliminary design used a 15 by 15 inch, 15.5 inch by 2.8 inch wing and a 12-inch fuselage and some small tail surfaces, both triangular shaped. And our second iteration, our actual one, matter of fact, had a very similar reflection of our initial design, except that the horizontal tail was now trapezoidal instead of the initial triangular shape we were looking to go for. We just wanted to increase the surface area and also just try to induce as much lift as possible. And then we realized that using this iteration, it didn't go quite as far enough. So in order to increase more lift, we use tape to angle the wing upwards in order to generate more lift. And we also um, enlarged this horizontal tail. And these trade-offs demonstrated the classic balance between lift, drag, and stability. The trade-offs were more lift, but more drag due to the tape and the added weight. But that being said, this increased the flight distance to roughly 30 feet, which is a big jump from the previous 20. Our final design used the same 15.5-inch high aspect ratio wing, a 12-inch fuselage, and a larger trapezoidal horizontal tail with a triangular vertical tail. All components were made from balsa wood with about 16 to 17 grams of clay added to the nose. You can see that right here. And then to achieve longitudinal stability, we adjusted the clay so that the center of gravity sat slightly in front of the wing's quarter short point. And that point would be about right here. Definitely not the best, but for what we had, I feel like we did a pretty good job. And then it is more or less an ideal position for stable gliding. And then with that, the aircraft avoided pitching up, it stalled less, and it produced a clean, predictable glide path. And then our wing area was about 43.4 square inches, giving us an aspect ratio of about 5.54, which does meet the requirement of 5. Our total glider mass was approximately 38.26 grams, with 22 grams being balsa wood, and this kept us well above the 50% balsa requirement. Our wing loading was 0.1366 grams repeating, or grams per centimeter squared repeating, which is significantly below the max allowable 0.5 grams per centimeter squared. Next, we estimated aerodynamic coefficients using our measured mass, wing area, and approximate cruise speed. And at typical glide velocity of 6 meters per second, which we estimated through the video and our calculations, we computed a lift coefficient of about 0.61 and a drag coefficient of about 0.057. And we use these equations on the right. This is the equation for the drag coefficient, and this is the equation for the lift coefficient. And then here are our flight results. This is just the video of our test 2 flight. I'm gonna play that real quick. So as you can see, it flew pretty well. There wasn't as much lift as we would have hoped for, but it did produce enough to actually get it past the threshold and then reach 40 feet. And for test one, the glider used minimal nose clay and had rougher surface finishing. It flew around 30 feet, but showed slight yaw drift and inconsistent pitch. And the test showed us that we needed more forward center of gravity and better alignment. And that leads us to test two, where we added some more nose clay. We cleaned the alignment and slightly adjusted the tail. And performance was much better, 40 feet now. It was much smoother and had a stable glide and straighter flight path. Just as the final reflection and summary, our final glider met all requirements and consistently flew well beyond the 20-foot minimum. The biggest improvements came from the center of gravity tuning, the tail resizing, and reducing surface imperfections. But that being said, if we did it over again, we could have tested more wing angles and dihedral early on. We could have tried reducing weight in the fuselage and experiment with slightly larger tail surfaces for even better directional stability. And also, we could have definitely sanded some more and roughed out the edges. But overall, this project taught us a lot about balancing structural constraints, aerodynamics, and iteration to improve flight performance. And these are just some of our references, which includes just a standard 16-step instruction for building a balsa wood glider and a tutorial for tiny chunk gliders, which are gliders, but more like darts. So thank you. Thank you for watching.